is very difficult for foundries to bring in all these different conflicting requirements of high voltage, high performance analog, high voltage power, and high density digital into single process technology. What we have done at Onsemi is we solve those problems, and that allows us to integrate all these different functions, features, in spite of their conflicting requirements into a single piece of silicon.
Welcome to today's ipXperience podcast, a very special edition with a new product release from Onsemi. Get ready, because this isn't just another product update. Onsemi is changing the game by merging 3 legacy solutions into one streamlined single piece of silicon. Onsemi is a leader in intelligent power and sensing solutions, driving technology that's at the heart of a more sustainable, efficient world. From electric vehicles to industrial automation, Onsemi is known for creating solutions that help power the future. Today we're joined by Vijay Rentala, VP of Advanced Solutions Group, CTO and On-Technical Fellow at Onsemi. Vijay has been a visionary in the semiconductor industry for over 2 decades, and he's here to introduce Onsemi's latest innovation. Let's dive in.
Vijay, over to you. Tell us about your platform and how it's disrupting legacy designs as on from the 3rd week of November.
First of all, Guy, thanks for inviting me and giving me an opportunity to talk about the upcoming announcement of Onsemi. Okay, now jumping into the announcement itself, very soon we'll be announcing the industry's first 65 nanometer based BCD platform that in our opinion is the most advanced BCD technology out there, that allows Onsemi to create products in the most advanced digital, high performance analog, and high voltage power, all in a single integrated platform, and providing solution to customers, allowing them to create new innovative system solutions that otherwise not possible prior to this announcement. So here we are with this announcement. Yes.
All right. So in very simple terms, explain to me, if I'm a design engineer and I'm listening to you saying that this is the announcement we're making, you've obviously targeted that at a legacy environment. So in very simple terms, explain what is the legacy technology that you've looked at and gone, right, we can improve that. So just explain in very simple design engineering terms, what is it today that design engineer in OEM, and in an OEM, and what specific type of OEMs are you targeting this at?
So if you look at any of the power, let's take an example. Let's take a power management example. It's easy to explain. Typically, you actually dealing with high voltages and high currents, and that requires, that is used to be designed in a specific process technologies that can actually withstand this high voltages, in simple terms.
Yep.
Now, but behind the interface of high voltage, there is also a high performance analog that used to be done, and today it is done as a separate integrated circuit. It's a separate chip by itself, and even before that, there is high level of computation that is required, which I call high density digital, and that is done in another solution, another chip, as a completely separate solution. So today's solution, if you look at any of the high powered applications, yes, there is the high voltage that requires a special process, but there is again high performance analog and high density digital, today done in 3 separate pieces. And the reason for that is each of those technologies require a unique recipe of process technologies that allows them to be the best at what they do. And it is very difficult for foundries to bring in all these different conflicting requirements of high voltage, high performance analog, high voltage power, and high density digital into single process technology. That has been the biggest challenge in the industry, and that is the reason why today's technologies, we open any of the high powered blocks inside automotive or industrial, you see multiple chips doing multiple stuff. The reason for that is it's really, really hard to integrate this technology into a single chip silicon because of some of the physics constraints that were posed. And I think what we have done at Onsemi is we solve those problems, and that allows us to integrate all these different functions, features, in spite of their conflicting requirements into a single piece of silicon. That's really what we do.
Very interesting. So in high voltage environments, so let's take automotive, let's take industrial, And today, in order to get best-in-class performance, you'd have to be taking each individual parts of those, which you described 3 individual parts. So let's just go through those again. Those 3 individual parts that you're looking at as a legacy. So just in a very discreet way, using that power word, discreet. Very. You almost know that I knew what I was talking about. Easily fooled. Explain to me those 3 very discrete parts that a design engineer would understand today. Just in a very simple way, one by one, 1, 2, and 3. Those are the 3 parts that you'd be using today.
Yes. So let's actually use an example, and I'm going to use an example that the kind of power management systems that is currently used in cloud compute or AI servers. You can put different names to it. So we have a system and to get the signals for let's call it the AI CPU today, which typically runs off approximately around 1 volt. So you have 1 volt. 1 volt is the CPU supply needed, but the incoming voltage coming from the wall all the way to the battery and all the way to the PCB, it's about 12 volts, between 12 to 48 volts. You could have a different voltage. Now you need to efficiently convert this high voltage into a very low voltage, but very high. So this is the requirements today. But to do that, we have to do today in the current system, we are using discrete, what we call smart power stages. And all their job is actually take this 12 volts and efficiently convert to 1 volt as a single on-off transistor. That's what they're doing today. But to drive those discrete stages, we now have an analog block sitting before that drives this, what we call the transistors in a very what I consider unique way, because it actually requires high speed level shifting and ability to tolerate high voltages while driving these large capacity loads, which is what I term it as high performance analog. Now, the input to this, the intelligence needed, where how much voltage and current is actually being driven to the CPU, is actually sensed and actually does a computation is done in another chip today, which actually does the computation and figure it out what should be the next stage for the FET needs to look like, and pass on the information to analog, which subsequently drives these large FETs. This is how the system is built today. So you have 3 systems.
Right.
We have a controller, we have the driver, and we have the FET. 3 different distinct units today in the system today. And why are they there today? They're there because each of them are designed and optimized for that specific operation. That's why they're so good at what they do. And they achieve efficiencies in the range of 99%. I've seen 99.2, 3, 4%, almost ideal conversion, which is great. And each of them are designed for it. But if you look at the board space, they occupy significant area. And most of the time, the energy is spent in passing on the information from the digital chip to the analog chip, what I call computation chip. By the way, the system is called multi-phase controllers, just as an example. Now, this system is actually, the energy is spent, the efficiency is lost in transferring the signal from one chip to another chip to another. Sometimes just driving the parasitics on the package, sometimes driving the parasitics on the board, and also losing efficiency because now you have to contend not just with the parasitics, the FET itself, but also the package and the PCBs that actually are in between. And not to forget, they also occupy significant space in a very space-constrained environment. If you look at the server racks, they are massive. There are hundreds of these components sitting around there, and they also contribute to heat. So now, how do we actually bring in all these different components that actually are designed to be specific from a functional perspective, the absolute best process nodes they need to be? That is how it is done today. Now, what Onsemi has done is change the paradigm and solve the fundamental problem of how do I integrate these 3 distinct, unique requirements needed for computation, which is the multi-phase controller, the digital multi-phase controllers, or the analog, it doesn't matter. And then the analog itself, which drives this high voltage signals to the FET, and the FET itself, which actually can work as the absolute best on-off switch. Now, what we have done is we brought all these technologies, and now we came up with a platform that can now serve from all the way down to 1 volts, all the way to 90 volts in a single process technology. Single chips of silicon can do this, and it's designed in such a way that it's actually modular, now the reason that I'm using this word called modular is because now it's up to the.
So just repeat that word. Just repeat that word.
It's called modular. Modular. Essentially, each module. I mean, we created the process technology.
Co-modular. Sorry, co-modular was the word I was trying to get to. Co-modular. Okay. So can I just ask a question? I just want to ask a question. So at the moment, the solution is these 3 discrete parts, which all, if you're managing your power, you've described extremely well. How you got those 3 discrete parts, best in case or best in class, I think was the word you used.
Yes.
Best in class was the phrase you used. Now, that's a very understandable proposition that you make there. I'd like to ask the question of, do you also have to do some special engineering with the implementing each one of them working sequentially together in your application? So you're not just having to understand the 3 best in class for my application. I'm also having to understand how I integrate those 3 parts to work together. So so it's not just a matter of choosing a product, it's understanding how you integrate them and get them to work together. So that sounds to me like it's not a simple solution. There is absolute engineering that goes on top of that. So you could just explain the engineering that has to go on, that is the whole point of having 3 parts. Just explain the background for that.
Yeah, so the background for that is you typically need a lot of computation in when you actually sense a signal. And by the way, the example I can also do a sensing application is an example. Driving, sensing high voltage, you require high voltage sensing, and you need a high performance neuron to make sure that the signals you're measuring are confident. But you also need to convert that into digital and do some computation to convert those signals and do some intelligent decisions and then feed it. So again, this is another sensing system example. But now going back to your question, each of these things requires a different kind of engineering to actually make sure each of those things actually perform best in what they do. As an example, you have digital. Let's start with the digital or computation. You call it computation. That requires typically. I mean, you heard computation in various in various ways. Now there's a buzz around AI. AI is all about computation. And if you look at the process technologies that we are currently being used, we are almost going to the atomic level. We're going down to angstroms and nanometers and things like that. The reason that we do this is because that requires massive computation and requires a different kind of transistors that allows us to perform these computations in a very power efficient way, so that you don't lose a lot of power because you're doing massive computations. And you need to make sure that you're doing all these things in a very, very small area. That means the number of transistors per unit area is significantly. That's why those things are done in a separate chip. Now, when we move to analog.
So just to summarize, then we have a scenario where you have 3 discrete parts, best in class. They all have to be integrated. Your word, sequentially engineered together. It's a very lovely phrase. Sequentially engineered together. That's a nice turn of phrase, because it implies a huge amount of nuance and intelligence and understanding and experience to be able to do that kind of thing. But you're then explaining that. So you've got the 3 discrete parts. You're explaining that there's a lot of engineering that makes them sequentially work together, and that they're also taking up a lot of space. And then in summary for the legacy, we then have to look forward, because we know whatever happens, AI is going to play a part in the future. So you have to understand, you have to be future-proof in some way, which is going to be power, heat, and space, essentially.
That's right.
So that's today's scenario as you have summarized today. So if you are somebody that is working with those 3 discrete parts, you understand what you're doing, they all work, but there's a lot of clever stuff that goes on behind. And then Semiconductor have come along and gone, hang on a minute, we can do this in a cleverer way. So first of all, we replace the 3 parts, which is less space, not needing the sequential engineering. And then we are offering a modular solution that goes up all the power scales that you would need that you do. So that, I think, summarizes the legacy scenario. So now let's look at, actually in a little bit more detail, the platform that you're announcing, what it's called, and how you've solved that problem.
Excellent. So I think, by the way, thank you. You did a much better job summarizing than what I could. Thank you for that. So,
well, I got the input from you.
Yeah. So I think is the right words. So I think now that you're putting in your words, the way you described it, yes, we have a change here that we have three distinct parts doing distinctly three different functions, each of them efficient at what they do. But the penalty, like you described, is board space, efficiency loss, and also something subtle but not very obvious. Because they're discrete and they're actually on the board sitting in different places, there are system topologies that are forced on us, not by choice, but actually by the fact that just mere fact that they're actually in a different parts of the PCB. Sometimes two of them are in the top, one of them in the bottom.
Yeah.
Some of them is sitting somewhere else with a cable connected. Not that I'm recommending that, but there are system topologies that are forced on the designers and the system designers primarily. I think what we recognize is that if we can actually find a balance, and I'm using the word balance not to say that we actually manage to make everything perfect and we're going to have a 2-nanometer performance of digital and multi-volt performance of power on the same chip. What we have done here is we have done significant engineering to actually find the right optimal balance between the specific needs of what requires high-density digital and without compromising the high performance analog and power. That's really what we have done. And now, what that does, obviously, is it solves the problems that you described earlier, which is board space, the unique space of how we can actually integrate the functions. But I also bring in capabilities that otherwise not possible, because now you're not sitting somewhere on the PCB and where it is difficult to sense what is happening on the other side of the power. It's actually now you're literally in a single chip driving what I call micrometers versus centimeters on the board, because on the chip you're driving micrometers, if you think about it.
Yeah.
So that basically means your losses, or parasitic losses, are going to be significantly lower, improving the system efficiency in the case of power management system. In the case of the sensing system, your actual fidelity will actually go up because you're not picking up the noise along. Now,
so can I just draw you back, because I think you made I think you phrased something very, very nicely. And I think it's worth repeating for our watchers and listening. You talked about the trade-offs, okay? So you were very open about this idea that if I'm replacing 3 chips, there's going to be a situation where we are not going to get it absolutely perfect, which I think everybody would understand. But you had a very neat phrase to say, these are the parameters by which I start, and this is the parameter by which I'm then going to get to. And you had a phrase just going back about a minute and a half where you said, these were the parameters that we understood. So could you just repeat that so that everybody's very, very clear? Because that shows an understanding that On Semiconductor understood what the design engineers, the first question a design engineer will ask is, so what are the trade-offs here? What are the trade-offs and what are the parameters? And you had a very nice sentence that just described that very succinctly. Could you just repeat that sentence? Because
I apologize which sentence you're referring to. But I'll try
we'll come.
Yeah.
Yes.
Okay. So I think we talked about these 3 unique requirements, right? We have the computation you need a high performance analog and high voltage power. We have 3 distinct unique requirements. And in the case of power management system, the sequence is you have the computation, analog, and power. In the case of sensor system, it's high voltage power, analog, and power. It doesn't matter which way you go. It's the same thing, but it's all about where you're sensing and what you're driving. Now, in each of those systems requires very unique requirements, and in today's system, because each of them are treated uniquely, we ended up with essentially a 3-chip solution. And what we are trying to do is find this optimal balance of what is the amount of computation you need to actually perform calculations in a smart way, instead of just using what I know today and saying, okay, I'm going to just split them into 3 separate solutions and I'll figure it out. Now, instead, we're actually proposing a system solution here. We're bringing in these 3 entities into a single chip, improving the efficiency of the system itself, not just the space, improving the efficiency, but the subtle thing I refer to is now creating system topologies that otherwise even not even thought of before, simply because they're sitting in 2 different places or 3 different places in some cases.
Yes.
So this is what the uniqueness of the technology we're bringing in today, which is going to create opportunities for system designers to think about, hey, now that I have this technology available that was not available before, how do I think about these systems differently than before?
Yes.
Which is very subtle. Yeah, go ahead.
No, this you've used this phrase quite a lot going through here. System topology. Not heard that phrase before, but again, you've come up with some quite all the way through this chat. You've come up with some very interesting phrases. So, system topology automatically leads me to say, okay, I understand I understand the legacy, I understand the concept, I understand why you've done it, and I'm beginning to understand the advantages. I think what the watchers now would like to understand is, so what does that look like in the real world? That must lead us then. So if I'm going to have this system topology, that instantly leads to the idea that instead of having these 3 discrete chips over on the board doing their own jobs, all interconnected, but they're in different places. And what you're saying is, with a more efficient system topology, which is 1 chip for the 3 solutions, that gives you so many different options for how you lay the board out, and your imagination then can lead you in other directions. So let's just go through now how that system or that platform that you've announced actually expresses itself in terms of products, because you talked about scalability. So from a watcher's point of view, you've described the parameters very nicely, but now I need to know the proof that you have products that go through that scale, and know that everything that, oh, is that me? Yes, it is, because Vijay's just told me he's got products in all these sections. So just run us through the product portfolio as when you announce it.
Yes, as part of the product portfolio, we'll be announcing a wide range. But I'll actually start off from the proof for each of the sub-units first, and then actually bring in the system together. As we are going to announce a range of series of high performance, what we call low dropout regulators. Essentially requires high performance analog to actually produce. These are extremely low noise and also have high performance in terms of the device, and of course very optimized for performance and cost. So now we have this, as we'll be announcing these things. We're also announcing level shifters, again going back to the high performance analog. Now on the other side of the spectrum, we do have solutions that actually leverage the high voltage piece of it. We have a product right now which actually is a sensor that actually drives a high voltage directly from our chip. Now, those products today exist. It's not a surprise, but the way they exist is what I consider is, because of the system constraints that I mentioned before, are designed to be. I don't want to use a strong phrase here, but I want to say that let's call it less intelligent. They're doing a basic task, perhaps doing very well, but they're just doing a basic task. But today we are actually going to announce ultrasonic sensor in this case, which actually drives the essentially it's a sensor that drives the high voltage and meets the regulatory requirements for high voltage. So now that is actually a proof of concept for the high voltage. Now, we are now coming up with the products on the other side for the digital. We are actually now integrating large digital that otherwise this kind of process technology is not even considered feasible. We have the ability to now integrating starting from a simple digital, small number of gates, to a really high performance systems where actually they can perform intelligent tasks, not just computation, perhaps extending all the way to accelerators like neural network accelerators in future. So we have products in development, and we have products we'll be announcing. Now going back to the system solution that you asked about, let's actually take this example of this sensor that I talked about. This sensor actually now has intelligence in terms of our computation, which is large digital, high sensitivity analog, and a high voltage driving capability, driving the sensor directly, all in a single technology. And that's what we're announcing today. And that will be part of our announcement, which is actually a sensor, which addresses your question that you're asking before. Now, one could ask the question, it looks very similar to the previous one with one big difference. This is way more intelligent than what it was before, because all it is previously things are doing is, think of it like a feed forward network. All you're just doing is passing on information. There is not much.
It was doing its job. It was doing its job.
Doing its job. But now, because you have the capability to do more, you're actually doing sensing and converting that information that you observe into something more intelligent than just doing what is supposed to. So this is the kind of differentiation we're bringing in. And that's actually one system example I can give. We also have, as an example, high performance glucose monitoring solutions, that this is actually very important for diabetic health. We were able to demonstrate that with this platform, we can actually build a high performance analog and computation on a single chip. Now, just want to caution you on one thing. Not every system need to have all three elements integrated. It's actually a system topology choice. And I keep going back to that. That statement.
Yep.
Wherever you need these different pieces, you can now start thinking topologies and saying, do I need analog and digital together with the power staying outside, or power and analog together with the digital staying outside because you need more computation? Or can I actually live with all of them in one single chip? And that's the example I've been talking about. So now you have the system just that you can bring it in. And the continuous glucose monitoring is a good example of the analog and the digital connectivity. Not the power piece, it's not needed in this case, because we don't want to be forcing things just because we don't need it.
Yeah.
In this case, we can actually build this kind of solutions. Now, if you look at our platform, on one side of the platform, you have this extremely simple building blocks like LDOs, amplifiers, level shifters, to all the way to glucose monitoring sensor, which requires digital and analog together, and to another level where you need digital, analog, and power in this ultrasonic sensor that I gave an example. So here is a platform that you can do all of them. And the interesting thing is, because the platform is modular, you can actually just build these topologies in a way, or these IPs in a way that it is reusable across the platform. You are not constrained by, if you build a particular solution for one thing, I need to build something from scratch. No, we can just copy and paste here, because it's a modular technology, that allows you to take the IPs from one and actually copy and paste another one. And because these IPs are proven, now you can actually build solutions in a much faster way than what was conceived before. If you look at any of the product development cycles, they're extremely long, but with our platform, we believe that we can actually deliver a solution to customer in a significantly lesser time to customer, allowing the customers to optimize their systems rather than focusing on what chips they need to make them.
Yeah. So I've got a couple of questions. So first of all, when you've used the word intelligent, because you've put everything into one module with the 3 chips, you're then able to offer, let's say, I don't know how you've done this, but just for the sake of having this discussion, almost like a set of IP libraries that allow them to sit inside there that you can take advantage of, that are already embedded in the system because it's all integrated, which then allows you then to do more interesting things either end of the input. Is that more or less what you're saying with this solution?
Yes, you can say that way. That's one way to describe it. But you also need to keep in mind, just because the IPs are there, we don't want to be just increasing the cost of the device by just adding these IPs. What I'm saying is we have this library of IPs that are scalable, that can put it in the platform anywhere you want, anywhere you choose to do. One could actually pick up the IP from one and actually take it for reuse from here to here. Again, this is not much for the from a customer perspective. It may or may not matter. What matters is the time it actually takes Onsemi to come out with the products is going to be significantly smaller, because we are actually allowed to reuse this platform across the board. That's the most.
I understand.
So this is more of, because I have noticed throughout my career, as the requirements are being gathered for a specific system, the system designers have some ideas in mind. But as the chips get developed, because they're multi-chip solutions, suddenly we observe that, I'm missing this piece from this. Now it goes back to design almost all over, and it'll be another cycle of learning to actually make the chip.
Yeah.
This to me is actually a wasted time if one is allowed to actually optimize the system, because the cycles we are talking about is 2, 3, 4, 5 years of building a complete system. But what if we give that time back to the system designers, where they optimize, tune the parameters in the right way, and then provide the requirements to Onsemi and saying, hey, here's the requirements that I'm looking for. Can you build a chip we'll be able to efficiently build this chip in a much shorter time because we have all these basic building blocks and built IP and we are able to bring them together. And because they are all in the same process technology, we don't have to worry about coordinating between 3 or 4 different scopes on one. So this is the value being in, yes.
So it's this whole idea of system topology, which is a phrase that you've used. And then because of the fact that you are the integrator of the 3 individual chips that have brought it into one system, that means that you're able to much easily move on and work out what you actually want to create with your solution, rather than having to do that engineering that we started off with at the beginning of the conversation, where you've got to be constantly working out how these 3 chips are going to talk to each other, integrate, which takes up a huge amount of engineering time. You've already done that, and all they've got to do is choose the IP that goes into that module, and then they're good to go. Is that probably a totally oversimplified description of what you've done? But for the sake of this discussion, does that encapsulate what you've done?
Absolutely, yes.
Perfect.
That's actually, in turn, that's what we've done. I think that I did. I'll give you a very simple example, a very useful example that I encountered recently. We have, I mentioned to you the power piece, high voltage piece, typically tend to actually consume a lot of current, a lot of power. And that means that particular building block is expected to operate at a very high temperature. I'm just giving this an example.
Yeah.
And because it's actually working at a high temperature, the rest of the blocks are not. Now, the behavior, if you measure the current or the voltage in that building block, is going to look different because the temperature profile of that high power block is different than the temperature profile of the low power block. So we tend to have, if we're trying to measure the current at any given time, we're going to end up with an offset or a difference between what it's supposed to be versus what its reality is. Now, in this system topology that we're building, first of all, the platform is by design designed up to operate up to 175 degrees centigrade. The entire chip is expected to operate at 175, which is very unique, automotive grade 0 qualified. But now think about this scenario where you don't have the problem of the chip, the power is actually operating at 175 and the sensing is done at low temperature, which actually creates this offset. Now everything is actually working at the same temperature. I'll be able to very accurately measure current going through the power fetch and able to actually make intelligent decisions. Now suddenly, instead of making an assumption that the best I can do is, 5%, 10%, whatever the number may be, I can accurately measure it to the less, almost a lower single digit accuracy and actually make system trade-offs. Now I can now operate the entire system at its full potential without actually accounting for the difference in measurement. Again, this is a very different thinking, and this goes back to the choices that we made by building the platform. It's modular, high temperature qualified, automotive qualified. These are done for purpose.
And that's your whole. It was about 15 minutes ago. You said it's all about system topology. That's what it's all about, because that enables you to have a completely different way of looking at the problem that you've got that you probably didn't think you could do when you were dealing with 3 discrete products. And you said that very early on. So that summarizes that really, really nicely. So the final question is, people will have watched this and the first thing they're going to go is, yes, that's me. Yes, I understand what's going on here. 3 chip solution, 1 modular solution, system topology, versatility, IP availability, so that I can make my life easier and focus on the things that I actually want to do, which is create great products. Somebody's going to be saying, I want to evaluate this. So is there an environment that they can get hold of and look at, plug in today, and see how this modular system performs versus their 3-part system?
Yeah. So we will be releasing, as part of the announcement, we'll be releasing a slew of products, and the products will be accessed on Onsemi.com, where one could actually order these parts and actually start using those parts in their system and start building system solutions like that. I think we are announcing 7 or 8 products. I don't remember its number, but essentially to demonstrate the capabilities of the platform, we are actually announcing a range of slew of products in both the high density digital, high performance, high design, and of course a mixing these components in different products. And I think that we have multiple products that are coming in. There will be product pages as part of the announcement. One could actually go and access that, and you would have access. You would be able to get your hands on the products and actually start putting in your system and trying to find system solutions.
Excellent. And I just one lot. I mean, I'm sure this is part of it, but when you go to look at that evaluation, I take it you will be asking some very basic questions about your current system in terms of its power and its voltage and all that kind of stuff. So you'll fill that in, and then what will come out is this is the best modular system for you to evaluate against the parameters that you've just put in. I'm assuming that is what will happen.
Yeah, I think the data sheets actually will describe, and the example product, the usage examples will describe how this thing can be used. And one could actually look at those topologies and say, hey, that's exactly what I need. And I can actually use it for my system.
Excellent. Well, Vijay, this has been an absolutely fantastic conversation. We thrive on the whole concept of disruptive technology. It's the whole point of our platform. It's the whole point of our community. And when somebody comes along like Semiconductor and says, do you know what? I think that we can replace the idea of system topology, new phrase that I've learned today, system topology. We can simplify the whole concept of taking three discrete products, how you integrate those three products, which is very complicated, how you make them work in your individual system. And we're going to take it down to one modular system that you can then focus on the outcome of your individual project to explore new ways of doing things. I think that's been a wonderfully interesting discussion, been a wonderfully disruptive environment, and we are very privileged to have chatted to you today and have this announcement from Semiconductor from the first day of Electronica. Thank you very much.
Thank you very much, and thanks for giving me the opportunity. Really appreciate it.